Welcome to the lecture titled Applying Identification of TITO Systems. Earlier we have described a set of powerful equations those can be used for the identification of stable, unstable and integrating process models. Now, those stable, unstable and integrating processes are basically of single input, single output type. In today's lecture, we are going to discuss about the identification of two input, two output processes or systems. Now, this will be basically an offline identification technique, and this technique is very much different from the earlier techniques in the sense that we shall handle or deal with a TITO, two input, two output system. How two input, two output systems are different from the single input, single output systems? In the single input, single output systems, we do not have any loop interaction, whereas in the case of two input, two output system, we have got loop interactions, and that makes the difference. And if the loop interaction can be handled suitably or properly, then the identification technique we have discussed earlier can easily be extended for the identification of TITO systems. Now, how a TITO system looks like? It has got at least 4 subcomponents given by G11, G12, G21 and G22, and the inputs to the systems are, there are 2 inputs. So, the input signal here can be given by U1, the input signal over here can be U2. Similarly, the system has got 2 outputs shown by Y1 and Y2. Now, the same TITO system can be represented in the block diagram form as a block having 2 inputs. These are the inputs and 2 outputs. Now, it appears very simple, but when there is enough or sufficient loop interaction between the subsystems, then the TITO system appears to be very much different from that of a single input, single output system. Now, these loop interactions are shown by the transfer functions G12 and G21. Had there been no G12 and G21, definitely one can employ 2 relays for the decentralized control, of course, or for the decentralized relay control. 2 relays could have been easily employed here in this fashion. So, let me add the 2 relays here, and I can take the feedbacks from the output and get the simple relay control system for the TITO system. But what happens due to the loop interaction, the outputs Y1 and Y2 that we shall measure to estimate the parametric models or models parameters of the transfer function models will not be straightforward, in the sense that because of the presence of G12 and G21, what will happen? The Y1 will get affected by the loop dynamics of second loop, and similarly Y2 will get affected or will be modulated by the dynamics of loop 1. So, that way the loop interactions play a major role, and one must take care of enough effort to either get rid of the loop interactions or to devise suitable techniques such that the loop interactions can be minimized while conducting a closed loop relay control or relay test. Now, let me describe the TITO system a little bit more. A TITO system, when it is presented in the decentralized control form, how it is shown? I will have G11, G12, G21 and G22. Outputs are Y1 and Y2 over here, and inputs are U1 and U2. Now, what we have the loop interaction. So, we will get this added over here, and due to that we will have additional signals coming from the other loop. So, this is how we develop the 2 by 2 or 2 input 2 output system. Now, how relay control is effected here? A relay is added here, another relay is added here, and then the loop is closed. Of course, you will have negative feedback here. So, please allow me to put the reference inputs as well, set point or set value 1 and set value 2. So, this is how you get the decentralized relay control system. In this decentralized relay control system, how to find the dynamics of the TITO system in terms of either is frequency response characteristics or any other characteristics. So, initially what is done? Basically, the output signals are measured. The output signals will be sustained oscillatory output signals. So, they can assume different form like this. Now, if the loop interaction is sufficient, then the frequency of the output signals y1 and y2 could be different. If the loop interaction is minimal or minimum, in that case I can have y1 and y2 having almost same frequency. Okay? And so, depending on the loop interaction, it is expected to get the output signals with different frequencies or same frequencies, same frequency. Okay? Then how generally people identify the transfer function model? They collect the limit cycle data. So, collect limit cycle data, then do the frequency domain analysis and then use the Fourier series analysis and find out the dynamics G11 j omega, G12 j omega, G21 j omega and G22 j omega. So, this is how generally the decentralized relay control is used to identify the dynamics of a TITO system using of course, the Fourier series analysis. But we are not going to discuss this in this lecture. The main reason for that is that this procedure is quite cumbersome and not straightforward. It is very difficult to, unless you go through a series of analytical expressions which are often very difficult and quite nonlinear in nature, it is not easy to make out how the transfer function models can be obtained. So, that is to avoid that, I will present some simple technique that can be used to identify the dynamic models for TITO systems. Now, allow me please to write down the decentralized control system once more. Decentralized TITO system, where I shall describe the TITO system dynamics in the form of G11, G12, G21 and G22. Again we have got the output from the blocks added in this form. And the input U1 is passed on to, so that way I will have this in the second loop and this will go to the first loop. Okay. So, this is the TITO system now. Then when it is connected with a controller, the controller could be a nonlinear or a linear one. So, let me connect a controller of the form C1 here. and C2 for the second loop. So, with these controllers we can have the closed loop system shown as this is y2, this is y1, negative feedback and set values S1 and set values S2. So, this is how I develop a decentralized TITO system with two controllers in the loop. So, these decentralized controllers C1 and C2 will result in different type of transfer function models. Now, in place of the transfer matrix which has got 4 elements G11, G12, G2 and G22, it is possible to find the transfer dynamics between Y1 to U1 and Y2 to U2, or indirectly speaking this dynamics can be equivalently represented by two subsystems given in the form of U1 Q1 Y1 and U2 Q2 Y2. So, whole dynamics, the closed loop system I have shown over here can equivalently be represented in this form, and if that is so, if that is possible, in that case what happens? Now, one can easily employ a relay here to identify the dynamics of the two subsystems. So, I can put one relay over here, I can put one relay over here, and then I can have the relay test, and consequently the parameters of Q1 and Q2 can easily be estimated. So, this is what we are going to do in this lecture. Basically, how can we develop model such that instead of having loop interactions or instead of representations of TITO by a transfer matrix, we can have two single input, single output dynamics for the whole TITO system, and that is the beauty of the technique. So, once we develop the technique for the upper case, then it will be extended for the lower case as well with very ease. So, what will be Q1 now? So, before connecting this, so what is Q1? Q1 is having the input U1 and output Y1. So, please say the input U1 and output Y1. So, how can I find this one? This is possible provided I consider this part of the So, I will begin with this. Okay. So, this will basically give you the ratio between Y1 upon U1 or equivalent transfer function, single input, single output system dynamics for this, including that the effect of the interactions. Okay. So, I am going to find two equivalent subsystems. So, that equivalent subsystem Q1 will be now the ratio between Y1 to U1. For that I have to consider this. So, I have to break the loop as well. So, if I break the loop over here, then I do not have this, okay. Then it will be possible to find the ratio of Y1 upon U1. How can you find Y1 upon U1? You need to redraw this a little bit to find the ratio between Y1 and U1 and subsequently Q1. So, to find that one, what we have in the reduced block diagram now or the modified block diagram, G11 that will get connected, no signal is coming there, rather your G12 is coming over here, because this is basically this signal is the same as U1. So, U1 is passing on to this one, and that then we are getting the lower part. So, what I will have here basically signal U1 and then I have got the block G11 and I have got the output Y1, but the output is made up of two outputs, one given by the interaction. So, G21 will come into picture and this is getting connected over here. So, basically I have the summer here, then I have got the controller here C2 and G22 and we have got G12 coming from there. So, G12 is adding over here and I have got this. Okay. So, this will give us Y1 upon U1. So, how can we reduce this block diagram now? This can be reduced further considering C2, if I take minus C2 over here. So, if I please allow me to write minus C2 G21 then this block will go out, then this will be having minus C2 times G22. So, I will have here minus C2 minus C2 G22. Okay. So, again this full dynamics again can be given by 1 upon. So, this part I can represent by 1 upon your 1 plus C2 G22. Okay. So, this will get added. So, ultimately how much Y1 upon U1 will be G11 coming from here minus C2 G12 and G21 upon 1 plus C2 G22. Okay. So, this is how with the help of signal flow graph or reduced block diagram or block diagram reduction technique, it is not difficult to obtain the expression for Q1H. Q1 is equal to the ratio of Y1 upon U1 is equal to G11 minus C2 G12 G21 upon 1 plus C2 G22. Okay. So, this is very important. Why we are doing all these analysis? Please look carefully the expression for Q1 or the subsystem we have developed or we have converted the two input two output system into a system which has got two SISO transfer function models now. Okay. And all the loop interactions, all those things are taken care of, all those are present here. Similarly, I will get an expression for Q2 as G22 minus C1 G12 G21 upon 1 plus C1 G22 G11 C1 G11. Okay. So, this is how we find two SISO transfer functions for the whole dynamics or for the dynamics of the TITO system. And this is very important for us in the sense that all the analysis we have discussed or derived, all the equations we have derived so far can easily be extended for identifying the dynamics of TITO systems, provided it is possible to convert the dynamics of TITO system into some single input, single output dynamics or single input, single output transfer function forms. Okay. So, Q1 is this much now, then when C2 is a large number, that time what will happen? Q1 will be equal to Y1 upon U1 is equal to G11 minus G12 G21 upon G22. Okay. When C2 is a large number, then Q1 can be expressed in this form. And when and basically the loop interaction has gone out. I can say that when C2 tends to infinity, basically we have been able to overcome the loop interactions between the two loops, or the loop interactions have been reduced substantially, so that relay tests can conveniently be conducted, and the parameters of the two models, the two transfer function models, which can be given by the equivalent dynamics. The equivalent dynamics now will be for Gs, the dynamic was given by G11, G12, G21, G22. Okay. Now, its equivalence will be given by a transfer matrix of the form Q1, 0, 0, Q2. Okay. So, once it has been possible to convert this TITO dynamics into this equivalent diagonal form, then it will be very easy to extend the relay feedback technique we have described for the single input, single output system. So, how can we make C2 tends to infinity during the relay test? Yes, that is possible, provided we employ some modified relay in place of the classical ideal relay or relay with hysteresis. Okay. So, I shall present you now a modified relay, which will have a relay in parallel with a gain. Let the gain be given by K, and a controller Cn, a controller Cn. So, this gives a modified relay. The modified relay will be used now for identification of TITO systems. Why we are injecting so many elements along with the conventional relay? What are the benefits we are going to get from this arrangement? That will be apparent when I put the modified relay in the TITO decentralized control system. Now, this Cn can assume the form of a PI or PID controller. Let us start with a simple PI controller. So, when Cn is given in the form of Kp plus Ki upon S, and in steady state, S tends to 0, that we know. Okay. Then Cn can assume a large value in steady state. Okay. So, the modified relay is going to help us in reducing the loop interactions. With the help of Cn that is present in the modified relay, it is possible to reduce or eliminate the loop interactions we have between the two loops of the TITO system. Okay. So, this modified relay will be used for conducting relay test. Now, how this modified relay can further be represented? This is same as a relay with the gain shown in the feedback path with Cn. Okay. Now, we will connect the modified relay with the TITO system. So, please keep in mind. So, when I have got my Q1 here, okay, because the loop interactions have gone, with the proper choice of Cn, it is possible to eliminate the loop interactions, and the TITO system can equivalently be represented by a transfer matrix which has got only diagonal elements Q1 and Q2. Then in that case, we will have our Y1, and this gives you a negative feedback, because when Q1 is connected, output of the Q1 is fed back in this form. This is how the relay test is conducted. Now, the equivalent form of that can be represented in this form, and subsequently you have got the negative feedback over here. So, the equivalent block diagram of the upper one is given below, and interestingly the gain I had connected in parallel with the relay is found to be available in the inner feedback path. So, additional advantage for going for this modified relay is that since we have got inner feedback controller now, if Q1 is unstable or having its pole located in odd positions, can be relocated at some suitable positions at the with the help of K1. Okay. So, now we can relocate the open loop unstable poles or odd poles or oddly located poles of Q1 at some convenient locations with the help of K, because for this dynamics which the relay sees can be equivalently be given by a transfer function of the form C n Q1 upon 1 plus K C n Q1. So, please keep in mind the roots of open loop transfer function Q1 can be suitably relocated with the help of the gain controller K. So, we have got so many benefits from the use of the modified relay, or using the modified relay it is possible to get so many benefits or a number of advantages. Apart from reducing the loop interactions with the help of Cn, it is possible to relocate the poles of Q1 at suitable locations with the help of the controller K. So, that is where I will go for this modified relay for conducting relay experiments. Now, this will be the block diagram that will be used finally for identification of 2 input 2 output systems. So, please observe carefully, this is the 2 input 2 output process or system dynamics given by G11, G12, G21 and G22. Okay. Now, what are these? These are the load disturbances, static load disturbances. So, D1 and D2 stands for the load disturbances present during the relay experiment. So, in spite of having load disturbances, I do not mind, because I have got a controller PI controller while conducting the relay test, the effects of load disturbances can be nullified or can be minimized, okay, or can be eliminated even with the help of the PI controller. Therefore, the use of modified relay results in multiple benefits. It can avoid the ill effects of load disturbances also while performing the relay test. So, if you connect the switches to 1 for both the loops, then a standard relay will be there in the decentralized relay control system. So, we will have 2 standard relays. When we connect to the second position, when I connect to 2 now, then the TITO system is subjected to modified relays. Okay? And when you connect the switches to the third position, then you get normal operation of the TITO system. So, to set the parameters of the PID controllers that we have got, decentralized PID controllers that we have got for the TITO system, it is first necessary to identify the transfer function models of the dynamics of TITO process, and based on the transfer function model parameters, the parameters of PID controllers are set. Okay. So, initially what will how it will be conducted, how to start with, where we have shown a standard or some standard relays also in the block diagram. Initially connect two standard relays and get the limit cycle outputs, and based on the limit cycle outputs use some simple formula technique such as the technique given by Ziegler's and Nichols. So, those technique can be used to find the parameters of C controllers C n 1 and C n 2, which are nothing but the PI controller. Okay. So, connect the switches to 1, let me repeat once more, connect the switches to 1 and find the dynamic model, and from that dynamic model set the parameters of C n 1 and C n 2. Then you connect the switches to 2. Now, when you connect the switches to 2, you have to start with some values of K 1 and K 2. So, can be chosen K 1 and K 2 can be chosen from intuition, or you can start with very small values initially. Okay. Then perform the relay test, then identify the transfer function models, and based on the transfer function model parameters set the PID parameters, and then switch on to 3 or connect the switches to number 3 and run the system, your TITO system. Then your TITO system will have a decentralized control system having suitable controllers in the loop. Okay. So, this is how automatic tuning of the controllers are done for the decentralized control of TITO systems. Now, how can we identify the transfer function models when modified relays are connected with the TITO process? That we shall discuss in detail now. Please allow me to take the dynamics of the nonlinear elements n 1 and n 2 in some diagonal form. N is equal to n 1 0 0 n 2, where n 1 is equal to 4 h 1 upon pi a 1 and n 2 is equal to 4 h 2 upon pi a 2. So, what are h 1 and a 1 in the expressions for n 1? H 1 is the relay parameter of n 1, relay setting of n 1. Similarly, H 2 is the relay setting of n 2, and when n 1 and n 2 are available, then we will have sustained oscillatory output for the TITO system. Measure the peak amplitudes of the two output, and two outputs will give the two peaks A 1 and A 2. So, A 1 is the peak amplitude of the output signal, peak amplitude of Y 1, the first output of the upper loop, and A 2 is the peak amplitude of the output Y 2. So, please see Y 1 will result in A 1 and Y 2 will result in A 2. Measure the peak amplitudes and then you get N. This is how N is obtained. Similarly, please allow me to write the gains in matrix form, diagonal form, given as K is equal to K 1 0 0 K 2, and the controllers C n 1 and C n 2 are described by two PI controllers of the form C n 1 is equal to K f 1 1 plus 1 upon S T f 1 and C n 2 H K f 2 1 plus 1 upon S T f 2. So, these are the PI controllers we have in the modified relay. So, with the introduction of K, Cn and N in diagonal form particularly, it becomes very easy to get the dynamic equation for the TITO system under relay control. So, now we shall describe in detail the estimation technique when the relay test is performed. So, two SI/SO transfer functions with delay are estimated based on the limit cycle data. What do we mean by the limit cycle data? We measure A1 and A2, of course, with the help of the relay settings of H1 and H2. Now, let the transfer matrix that is going to that is to be estimated be given by GMS. The subscript M stands for model. The transfer function model matrix in transfer matrix form be GMS is equal to GM1S 0 0 GM2S with diagonal elements with diagonal elements 0. Okay. Now, the two transfer functions in general form can be represented by GMIS is equal to KPI upon 1 plus STI square e to the power minus theta is. So, for all I is equal to 1 to 2, I will get two transfer functions. Okay. So, this is how the dynamics of the 2 by 2 or 2 input 2 by 2 system can be identified by the dynamics can be identified by two single input single output subsystems which have got the transfer functions G1 GM1S and GM2S. Now, the transfer functions have got the parameters steady state gains given by Kp1 and Kp2 for the two loops and the time constants given by T1 and T2 for the two loops and the delays given by theta 1 and theta 2 for the two loops. So, how many unknowns are there? So, we have got basically 6 unknowns for the dynamics of the TITO system. How many measurements we are making? Basically, we are making the peak amplitudes. So, we are making so far we have made 2 measurements only. Now, further measurements will be made and that will be then only it will be possible to estimate 6 unknowns associated with the dynamics of 2 input to output system. Now, the steps I shall follow for estimation of the parameters are given here. In step 1, the steady state gains are calculated using the formula Kpi is equal to yi 0 upon ui 0. So, the steady state values of the output signal y1 0 and y2 zeros are measured. Similarly, the steady state values for the input signals u1 0 and u2 0 are measured. So, how many measurements have been taken so far? 1, 2, 3, 4 and A1 and A2. So, please keep in mind we are making 6 measurements now. So, with the help of 6 measurements outright we estimate 2 parameters of the transfer function matrix, those are the Kp1 and Kp2. So, with the measurements of 4 values now it is possible to estimate the 2 steady state gains outright. Okay? And when you measure the the output signals in steady state conditions, please keep in mind set the value for one set point at 0 and the other at non-zero, then only you should take these measurements. So, to obtain correct measurement, what is to be done? Setting one of the set points at constant, setting one of the set values. So, either S1 has to be 0 and S2 non-zero, or S1 non-zero and S2 equal to 0, then you make the measurements of Y1 0, Y2 0, U1 0 and U2 0, and subsequently find the gains Kp1 and Kp2. Okay. Now, from the measurements of the peak amplitudes A1 and A2 and also the loop frequency omega CR. So, we are making one more measurement, keep in mind. So, how many measurements we are making now? We are making 7 measurements now. So, these are the 4 values, steady state values and 2 peaks. So, 4 to 6 and another one, the frequency of the output signals, and we assume that both the loops have got same frequencies. So, both the loops have got same frequencies. So, the loop frequencies are assumed to be of same. That means what? With the use of CN1 and CN2, we have been successful in eliminating the ill effects of interactions between the loops, or the loop interactions have been nullified, and subsequently it is possible to get the 2 loops having outputs with same frequency. Okay. So, this is how we make 7 measurements, and we are able to now estimate all the parameters associated with the transfer function models. So, with the measurements of AI and omega CR, 4 unknown parameters of the assumed plant models can be estimated, provided the ratio H1 upon H2 is not equal to 0. That means, both the relays should be present. So, both the relays settings must be non-zero. Okay. With non-zero relay settings, it is possible to measure A1, A2, omega CR, Y1 0, Y2 0, U1 0 and U2 0, and subsequently it is possible to estimate the unknowns Kp1, Kp2 and T1, T2 and theta 1, theta 2. Okay. This is how the identification of TITO system is accomplished. Now, let us go to little bit of analysis. Now, to obtain a stable limit cycle output, definitely the loop characteristic equation is to be taken care of. From the loop characteristic equation, I can get Gm Cn times Cn j omega CR times n plus k is equal to minus I. How we are getting that analytical expressions? I have got n here in parallel with the k, and I have got Cn here, and I have got Gm So, this will give a characteristic equation of the form I plus Gm Cn n plus k is equal to 0, and using that I get the analytical expression Gm Cn j omega Cr n plus k is equal to minus I when S is substituted by j omega Cr. Okay. Now, since we have got 2 loops, substitution of the diagonal matrices result in now Gmi of j omega Cr times Cni j omega Cr times Ni plus Ki is equal to minus 1 or minus, sorry, this will be minus, okay, for the individual loops it will be minus 1. That means, I can write this as Gm1 j omega Cr Cn1, please keep in mind j omega Cr times n1 plus k1 is equal to minus 1. Similarly, Gm2 j omega Cr Cn2 j omega Cr n2 plus k2 will be equal to minus 1. Now, this can be substitution of GMI, NI, KI and CNI will result in this expression. Okay. Just simply substitute the the expressions we have for GMI, NI, KI and CNI, that results in KPI times KCRI e to the power minus j times omega CR I theta I plus phi I upon 1 plus j omega CR T I whole square is equal to minus 1. Okay. Now, what is KCRI? KCRI is found to be NI plus KI times KFI upon cos phi I, and phi I is given by tan inverse 1 upon omega CR TFI. Where from all these things, the angles you are getting particularly, because I know that the expression for Cn, it has got a PI controller which is given by KFI times 1 plus 1 upon S TFI. Okay. So, that results in, when you express this in the complex form or in magnitude and angle form, then phi I is obtained. Okay. Now, equating the magnitudes and phase of left hand side and right hand side of the transfer function models. Now, if I take the magnitude of left hand side with magnitude of right hand side and phase of left hand side with phase of right hand side, then that results in the expressions T I is equal to root of KPI KCRI minus 1 upon omega CR, and theta I is equal to pi minus phi I minus 2 tan inverse omega CR T I upon omega CR. So, these are the two formulae associated with the estimation of parameters of the transfer function models, and from these formulae with the substitution of KPI, KCRI, omega CR, it is possible to estimate T1 and T2, and from the bottom also it is possible to obtain the values for estimated values for theta 1 and theta 2. Now, I will go to one example. Consider this example which has got a TITO transfer function matrix of this form. These two shows that the TITO system has got enough loop interactions. So, the TITO system is subjected to significant or strong interaction between the loops. Now, using the initial controller Cn of this form, the two PI controllers Cn1 and Cn2 of this form, I get the Q1 and Q2. I obtain the Q1 and Q2s, or the models are estimated. Okay. So, we will estimate the models, and now for the original process, the analysis gives us Q1 and Q2 of this form. So, simply substitute, we know that Q1 is equal to G11 minus G12 G21 upon G22. So, that will result in this form, and Q2 will give this expression. So, now to compare the efficacy of the identification technique, it has been the Q1s and Q2s are obtained. Okay. This is what we get from the original TITO system dynamics, and we have also identified the system parameter models Q1s and Q2s based on our technique. Now, what are those two Qs? If you look at this diagram, the dotted one gives you the original system or Nyquist plot for the original system, and the solid one for the identified system. And as you see, for the loop 1, they are not far off from each other. The third one actually shows the Nyquist plot given by some other technique. So, ours is definitely the better one, because it is approaching the original system's Nyquist plot. Similarly, for the loop 2, rather we have seen that the Nyquist plot for the original system dynamics and the identified system dynamics are very much in agreement, and it shows that the identified technique or the identification technique is quite efficient. Let me summarize the lecture. So, we have described a method for offline identification of TITO process dynamics. Now, model parameters can be estimated using limit cycle data, steady state outputs and the set point values, and further accuracy of identification depends on the efficacy of the modified relay. So, efficacy of modified relay means one must use correct CNIs or CN1 and CN2, appropriate CN1 and CN2 to eliminate the ill effects of loop interactions during relay experiment. Now, how to reduce the loop interactions during the identification techniques? One way is that by employing modified relay, as we have discussed here. So, you can use modified relay to eliminate the loop interactions between the two loops, or you can use some output filters that can also enable us to reduce or minimize the interactions between two loops. That is all in this lecture.